All right, let's look at the definition of the derivative function. Our objectives is to understand the definitions of the derivative and use algebra techniques to find the derivative and find equations of the tangent lines at a given point, or a given point of tangency. Now, you've all heard of trajectories or a path of motion. So there are motivations to discover or to wonder how tangent lines or tangent lines tangent to a trajectory is very useful. In this case, the tangent line here to a trajectory is actually indicating a certain direction that this little cart is going. So as it turns, and then as you can see, the line of tangency will also point where this car is going. Now that is a motivational idea of vector calculus. But in general, I mean, if we're just talking about functions, the tangent line of a function could tell you that if the slope of the tangent line is positive, we know that this function is actually increasing from left to right. So notice the slope is positive, then this function here is actually increasing. And then what happens right here when the slope is 0? Well, the function is neither positive or negative. I should say the slope is neither positive or negative. That means that function is not increasing and it's not decreasing. But what if the slope of the tangent line becomes a negative slope? Now that line has a negative slope. What do you know about the function? The function is currently decreasing. So there's lots of motivations to study tangent lines. For further investigation, especially if you're curious, go ahead and use Desmos and follow this exercise so that you understand what a secant line of a function is and what a tangent line of a function is. And you want to do that before we actually dive into the formal definitions of the derivative function. So go ahead and do that. Take some time, pause the video, exercise this Desmos idea, and then play around with this so that you get a very good sense of what a secant line is versus a tangent line. Now, when you're ready, go ahead and unpause the video and we'll start discussing the definition, okay? The definitions of average rate of change. So here we go. Here's the definition of the average rate of change of a function. We're going to specify a closed interval here from a to x. And how do we calculate this slope? Well, it's actually simply the slope formula. Notice that is the slope formula from algebra that looks like y sub 2 minus y sub 1 over x sub 2 minus x sub 1. It's just that now the labels are a little bit different. We're just using a's and x. I should say a and x for our labels. Now, if we look at the slope of the secant line, which is right here, this is the secant line, and if you look at the slope, that's great. Now, you can obviously draw another secant line as x gets closer and closer to a. Maybe the x value is here. Then if the x value is here, then the y value is here, and you could draw another secant line. So there's another secant line. What if you get closer to a? Then the output is here, and then you could draw another secant line. And notice as you get closer and closer to a, you'll get lots of slopes of secant lines. And then ultimately, when you finally reach a, what do you get? Well, this process is called a limit. And you actually get a tangent line. And we're really concerned about the slope of that tangent line because the slope of that tangent line will indicate whether the function is actually increasing or decreasing. So this is the definition of instantaneous rate of change. As long as you let x approach a from both sides, the picture is indicating x is approaching a from the right side, but you could actually go this way as well. The slope of the tangent line is going to be the limit of the slope of the secant lines. So as long as you take more and more secant lines and you get closer to the point of tangency, you'll end up getting the slope of the tangent line. So this limit will actually give you the slope of the tangent line. Now, more importantly, what happens if you do a clever substitution? What if you substitute x to be a plus h? So notice this a plus h here. Take this a plus h. Wherever x was, from up here, we're going to put a plus h in there. So the slope of the tangent line becomes this limit where now a plus h is approaching a, and then we have f of a plus h minus f of a over what? Over a plus h, take away a. All this simplifies to a new formula, and that is the slope of a tangent line, where you now have the limit as h approaches 0 of this difference quotient. Now this difference quotient is including the point of tangency. But what if we want to study the derivative as a function? What if we wanted to study the derivative as a function? So the first definition right here is the rate of change with a point of tangency. But the next definition is crucial, because if we let x be a variable, we no longer talk about a as a constant. We now look at x as a variable. So if we find that this limit exists, then we actually have created a new function called the derivative function. So as long as this limit exists, using algebra and of course trigonometry and calculus, we will get something called the derivative function. We'll label this derivative function a little bit different. We can't call it f of x. Instead, we give this a prime notation, so that apostrophe is actually called a prime mark. And so f prime of x is also called the instantaneous rate of change of f of x at any x in the domain. So notice the difference between the two definitions. One of them involves a constant or a number, and the other one actually is talking about a function, and that is because x here is a variable. There are other notations for derivatives. These are also all very important. How do you read this? This is actually the derivative derivative of f of x with respect to x. Okay, so both of these are read this way. Okay, the derivative of f of x with respect to x. Well, specifically here, I should clarify this. This is actually the derivative of y with respect to x. So the derivative of y with respect to x. Make sure you understand how to read that. This one is read the same way, believe it or not, and this one is read the same way. So the last three notations there can be read the same way. They're all derivative of y with respect to x. And the first one there just says the derivative of f of x with respect to x. Let's go ahead and dive into an example where we're trying to find the derivative function. And then, if possible, we'll find the equation of the tangent line for the point of tangency. So the goal is to find the function first, then we'll talk about the slope of a tangent line at a specific a value. Let's write the limit of the difference quotient. And we're simply going to simplify this. We are going to need to write the limit notation, the LIM symbols. Now you may have wondered, is it necessary to check the form? The form will look like very small over very small, which is in fact indeterminate. So as you're practicing evaluating limits, you always check the form. Notice the very first expression is indeterminate. Now there's not much to this. You're just reacting to your algebra, and so you have to rely on your algebra experience, rely on your algebra mastery. You got to master algebra to really have a good chance of understanding calculus. And you may have actually done this in an algebra class before, where you just simplify expressions. We're trying to simplify more expressions here. Speaking of simplifying expressions, I need to take away f of x. And hopefully you see that some of these will add up to 0. Here we go. This term will add up to 0. This term and this term will add up to 0. And this term and this term will add up to 0. So what do we really have left? That's really what we have left. Notice there's a common factor of h. And you're welcome to check the form again. I've actually already checked it, so go ahead and check the form yourself. You're going to realize you still have very small over very small, which is indeterminate. So we have to continue with our algebra, because algebra is very, very magical. We have a common factor of h. We have a common factor of h in the numerator and an h in the denominator. Now, this is going to be very, very magical. We now only have a numerator that consists of negative 6x minus 3h minus 5. So h is our variable. If h is our variable, then this limit does exist as a function. We're ready to evaluate this. This has a determinant form of negative 6x minus 5. I'm going to put a period there. So notice our final expression is a brand new function. Therefore, the derivative function, f prime of x, is also the instantaneous rate of change at any x value. And there it is. Even though I circled the final answer, that's only the second sentence. It's really the first sentence that helped you get you that second sentence. So I'm going to circle that entire first sentence as well. Can we find the equation of the tangent line at a point of tangency? Remember a equals 1. So why don't we find that? Let's find the slope of the tangent line. By definition, it's this expression. Next procedure is we're now going to use point slope form. So we're going to use the slope, which is negative 11, and we need the point. The point is 1 comma, go back up here and put 1 in this function, put 1 in there and see what you get. Negative 3 minus 5, negative 8 plus 1, you get negative 7. Now we're going to use the point slope formula. to get the equation of the tangent line. Oop, I think that should be a 4. Yep, there's your equation of the tangent line. And since that slope is negative, we know the function is actually decreasing when x equals 1 or when a equals 1.